Right, this is the final video for chapter 5. We're going to go over some, overall themes and recommendations, and sort of foreshadow a problem that we'll solve in the future. So first off, bootstrapping, it turns out, is one example of a wide class of simulation techniques called Monte Carlo processes. So in bootstrapping, we randomly selected resamples of the original sample and calculated the statistic and thus generated a sampling distribution. This use of randomness means that bootstrapping is an example of a Monte Carlo process, which is using a random process to help solve a deterministic problem, like the expected value of something. Okay. All right, now, when doing bootstrapping, by the way, bootstrapping was a useless technique until modern computers became fast enough and enough memory to actually do it quickly. So like World War II, I think, is the first time these Monte Carlo processes, of which bootstrapping is an example, actually started to be useful. People before World War II knew that this was theoretically possible, but nobody had the time or the patience to run through like 10 to the 4th or 10 to the 5th resamples of a data set and create a sampling, an approximation of the sampling distribution. It would have been laborious, inconceivably laborious. But then modern computing came along and bam, suddenly the technique becomes incredibly useful because it's so quick and easy to do now. Okay, all right, so what are the recommendations for capital N, the number of resamplings to use in a bootstrapping process? Well, you should use at least 10,000 or 15,000. That's ideal for bootstrapping. Okay, so that's the 10 to the 4th, and then 10 to the 5th would be what, 100,000. So that'd be great. Okay. By the way, pause, copy, play. All right. So this one, hopefully, print might have got a bit small, but pause it, copy it down, play it. All right, so some miscellaneous bootstrapping comments. So sometimes aspects of the true sampling distribution can be determined without actually doing a bootstrap simulation to approximate the sampling distribution, okay? And we've seen this before. So for example, the mean of the sample, X bar, and the standard error, theta hat over root n, of a theoretical bootstrap distribution are, the bootstrap distribution should be centered on the original sample. So the X bar should be the mean of the original sample, and theta hat squared, the variance, should be, as we saw earlier, 1 over n times that sum, where xi bar is the mean of each resample. Okay, great. But just remember that X bar, the mean of the original sample, might not be a very good estimate of the mean of the overall population. Okay, so the bootstrap is centered on the mean of the original sample in general, but not necessarily having any relationship with the mean of the actual population. Okay. Okay, so we've talked about this before. Bootstrapping is good to estimate the spread and the shape of the sampling distribution. And the larger that original sample, this is the smaller n, the better. Okay. And there's some really good illustrations in the book that will help us see this, that I'll talk through in class. So when we do a bootstrap simulation, the bootstrap distribution has 2 main sources of random variation that's hard for us to control. The first is that one sample that we were given, somehow that was chosen from the overall population. So choose that sample differently, and you'll get a lot of variation in your bootstrap distribution. Okay, your bootstrap distribution will look quite different, perhaps, than it had with another original sample being chosen. And then when we actually do the resampling, that's a random process as well. So when you do your resampling on your computer on R, and I do it on my computer on R, we're getting different values, not by much, but we're getting differences. And that variation is due to just the randomness of how we resample. Okay. All right. Also, in one particular parameter, median, bootstrapping might not be very good at all. So when we get an original sample from a population, it's usually finite, 1,000 people or 3,338 high blood pressure individuals, a finite number, a finite amount of data in that original sample. This causes the bootstrap distribution to be a poor approximation of the sampling distribution of something like the sample median, okay? Because the sampling distribution is continuous, but the original sample was discrete. So when you think about the median of a continuous distribution, you're looking for the spot where 50% probability is to the left, 50% of the probability is to the right. When you think about the median of a finite number of values, then you're just looking for the middle value, right? And so you could guess that if I grab a finite data set from an infinite population, my median of my finite data set might have virtually no relationship to the median of that original population, okay? That's again, the problem with having a continuous object being trying to approximate it by a finite object. We saw that with the normal distribution. We needed a continuity correction when we were trying to use a continuous distribution, the normal, to approximate a discrete process or a discrete population or random variable. All right, last panel then, some foreshadowing. Cool. So pause, copy, come back. So this is a subtle but important point that we'll spend quite a bit of time on. In many distributions or populations, the mean and the variance are related to each other. For example, in a binomial distribution, the mean is n times p and the variance is n times p times 1 minus p, or in other words, it's the mean times 1 minus p. So the variance is a function of the mean. In the exponential distribution, the mean is 1 over lambda and the variance is 1 over lambda squared. Or in other words, the variance is the mean squared. So the variance is a function of the mean again. So this is called having a mean variance relationship. And that's a problem with bootstrapping if you think about it. Remember, bootstrapping is not good at estimating the population mean mu. It's good at telling us what the mean of the sample we were given is, but not what the mean of the population is. And then think about it, if the variance is a function of the mean and bootstrapping is garbage at approximating the mean, it's probably not going to be that great at approximating the variance either. And what effects does that have? I'll mention what effects that has. Okay, so the value of X bar, the sample mean to the original sample, will often impact the bootstrap distribution standard error, because standard error is square root of the variance, basically. And if mean and variance are related, then this value will impact that value of the bootstrap distribution. Well, the standard error impacts the bootstrap confidence intervals. So thus the original sample impacts the bootstrap confidence intervals. So this could be a problem. And there's figures like 5.19 and 5.20 that we'll talk through in class a fair bit that are basically showing that the bigger the original sample mean is, that leads to wider bootstrap distributions, like they just look wider as a bell-shaped, vaguely bell-shaped curve. This would then imply wider bootstrap confidence intervals. So that's sort of problematic. That inability to nail down the population mean means we've got an inability to really nail down the variance, which then affects our confidence, our ability to give you nice, tight confidence intervals, okay? All right. How do we account for this? Well, there's a distribution called the t-distribution, which you might have learned about in high school stat class or something as the student t-distribution. That helps us to deal with this issue, and we're going to study that extensively in chapter 7.